Welcome everybody. It's 8 o'clock again for Thursday, the 6th of February. Again, we are very pleased to have Dr. Andy French today talking about quantum, atoms and nuclear. Let me just remind you that these ideas are very complicated. It's also the year of the quantum this year. So it's a 100th anniversary since the genesis of quantum mechanics as we currently understand it. So today, I think this is a very special occasion, a week after the international UN announcement for the International Year of Quantum. These ideas are complicated. You're not expected to understand everything in real time. Indeed, after 100 years, we still don't fully understand quantum mechanics, but this is your introduction. So take it away, Dr. French.
Thank you very much, Professor Chung. So obviously this would be a very mysterious topic. There'll be lots of conjectures, but I'll endeavour to be discreet. There we are, quantum mechanics. That's my joke for you. So quantum, atoms and nuclear, welcome everybody to the BPH Show Computational Challenge seminar series. So as usual, I'm going to give you a little smorgasbord of mathematical models that can be enlivened by the transmutation of maths into code. Don't think you need to take notes for all of this. I would definitely recommend downloading this presentation. And the idea is have a think of all the models I'll present, maybe 10 or 12 of them. You might think, oh, I reckon I could do that one. I could turn that into a spreadsheet, or I could maybe code this up in Python or MATLAB or other languages. So kind of almost have a little sort of wish list of where you think this particular model is one that you could have a go at. And maybe with a bit more practice, you could have a go at some of the others. So do write some questions in the Q&A, and we'll go for a little whistle-stop tour of quantum mechanics, atoms and nuclear physics. So there's also if the moderators could put my website in the Q&A, that will be a direct link to this presentation. Okay, so let's make a start. So firstly, some history. This is an amazing photograph. So this is a photograph from the 1927 Solvay conference in Brussels. In fact, 28 Avenue Louise, Brussels, it says in the little bottom here. And there are pretty much anybody who is involved with the genesis of quantum mechanics, who was a major physicist at that time, is in this photograph. So if you've studied physics for a few years, you'll of course recognize Albert Einstein. You'll recognize Marie Curie, so the sort of elders on the front row, but you might recognize Werner Heisenberg. You might recognize Erwin Schrödinger. You might recognize Niels Bohr. Where's Max Planck? He's somewhere along here. This is it, Max Planck on the front row. All sorts of people. And once you've studied maybe at physics at university, you might study Mr. Brillouin or Knudsen or Paul Debye. So the names which make modern physics, these are the people. It's an amazing photograph, and I guess quite strange really that this was set up by Mr. Solvay, who was not the head of world physics at all, was an interested industrialist. I think that's true. So there we go. There's a lot of serendipity in science, but this is a team effort, which hadn't really happened until that point. But nowadays, you know, the Higgs boson discovery, I think there were several thousand scientists from CERN that were cited on that. So there we go. So team physics. So we're going to start off with a few facts about the atom. So if someone asks you how big an atom is, really a one-dimensional, it's about 10 to the minus 10 meters. Yeah, yes, that's true, but that doesn't really convey how small an atom is. So you need kind of a big marble, really. I've got these sort of crazy-looking sort of 60-sided dice that I have in my classroom. The sort of things that make Dungeons and Dragons really quite tedious. But that's about 3.6 centimeters in diameter. And so what you have to imagine the entire Earth being comprised of those marbles. So literally the whole Earth, as far as you can see, are those little marbles all the way down. That's a lot of marbles. In fact, it's about 4.4 times 10 to the 25 of them. How do we do that? Well, we divide the diameter of the Earth by the diameter of my marble and we cube it. Okay, so the 4/3 pies cancel on both sides, that kind of thing. Now, the number of atoms in a marble is about the same number. All right, so if you can imagine the Earth made of marbles, all right, the number of atoms that make that marble is about the same number. So atoms are very small. And no surprise, that really until just over 100 years ago, that atoms were not the orthodoxy, right? The discrete nature, my very bad joke at the beginning, apologies for that. The quanta in quantum mechanics implies discrete, all right? Sort of, and atoms comes from the Greek atomon, means uncuttable. And that goes all the way back to Democritus, so thousands of years ago. In fact, where we get democracy from as well. But really, you know, their concept of an atom is going to be quite different from ours. But nonetheless, we haven't been able to really say that atoms irrefutably exist until relatively recently. Of course, you know, the atoms that make our marble are not the only structure, of course. So from the Rutherford experiment, we now know that most of the mass and I guess half the charge, the positive bits, is centered with a nucleus, which is 10 to the minus 15 meters roughly wide. So another little example is that about a meter, about this sort of distance, right, sort of meter on the screen. So that's the nucleus. Then the outer reaches of the atom are 10 to the 5 times bigger, so 100 kilometers. So I'm doing this in Winchester, and 100 kilometers is basically London. So the electron in hydrogen will be, if my nucleus was here in Winchester, will be anywhere to Piccadilly Circus and all the way around. Okay, obviously it's not quite in all space, but that's the kind of sizes we're talking about. So the idea is that we are living in very, very empty space, punctuated by a few parts which have very, very high density. So how high is that density? Well, here's a nice calculation. I hope you've done it yourself. So, by the way, that's Anders Angstrom, a sort of quite a nicer painting of Mr. Angstrom, a little bit bigger than the angstrom itself, which is 10 to the minus 10 meters. So these are the masses of electron, proton, and neutron, numbers that you should know. Notice that the mass of an electron is much, much smaller than a proton. So if we take the average density of atoms, well, we could just pick a proton or a neutron, it doesn't really matter, and then divide it by, roughly speaking, the volume of an atom. So if we go for half an angstrom, just to have a little bit more precision, multiply it by 4/3 pi, that's going to be the volume of a sphere, and we get about 3,200 kilograms per cubic meter, which is that's reassuring because, of course, you know, density of water is about 1,000. The density of iron is a bit more than that, maybe 5,000 to 7,000. So in other words, the average density of matter that we experience in our world, you know, on our kind of scale, is the density of atoms. So, you know, if that weren't true, then that's a really big red flag about this model. Okay. However, if we took at the density of a proton or you know, the nucleus, because we have a factor of 10 to the 5, then because we're cubing it, that's going to be a factor of 10 to the 15 in terms of the densities. And well, what sort of objects have that kind of density in the universe? Let's that answers into the chat, please. What have we got? So what macroscopic objects have densities which are about 10 to the 15 times this, so about 10 to the 17 kilograms per cubic meter?
We already got a neutron star.
Yes, good. So yeah, exotic objects, these crazy objects in the universe. Well, it's not really that crazy because we contain parts of that in our bodies. In every single atom, in fact, we have what we call an exotic object, except it's very small. It's just a nucleus surrounded by mostly empty space. But, you know, in principle, you could squeeze all that together to a macroscopic star-sized object, and there we go. That's what a neutron star is. And who knows what's in the center of a black hole, but, you know, that gives us some ideas. Okay, so atoms. Now, of course, you will have all seen this. So this is Ernest Rutherford, nice early photograph of him, and the people who did the really hard work, Hans Geiger and Ernest Marsden. So one day you'll be research students and you'll have a fancy professor and you'll do all the hard work and they'll take the credit. But you never know, you might have a sort of a radiation meter named after you or something like that. So basically these guys had to stay in a dark room for a long time looking at a very small piece of kit. And I haven't actually seen the original one of this, but we're not talking about an enormous piece. So we're probably talking about a few tens of centimeters wide. So you've got a tube where you have your alpha source with some holes to collimate a beam of alpha particles. The rest of it's sort of evacuated inside. So there's a beautiful piece of machined metal here. And then you've got the fancy bit, a very thin piece of gold foil, not many atoms thick. And then the genius of this, of course, is moving the detector around in a circle. And so most of the time, so what Geiger and Marsden did is basically record, the positions of alpha particles via a detector at different angles for a long time. And the vast majority of them went straight through. So the angle of deflection is small. So when you're solving or doing your GCSE exams and A-level exams, you'll draw these 3 diagrams and discuss them. You'll have most of them go straight through. Some of them are deflected, indicating the positive charge of your nucleus, because we know alpha particles are positively charged, helium nuclei, and very occasionally some will go straight and bounce off. Of course, we don't just have one atom. Remember, there's going to be thousands. So it's not quite as mad as trying to hit a 1 meter object in Winchester with the equivalent of alpha particles going from here to London. So it's going to be lots of those. But even so, the stats are quite stark. So, without going into lots of detail, that's basically how Rutherford and his collaborators were able to determine the structure of the nucleus. So how might this involve with some modelling, you might ask? Well, here we go. I must admit, this is not the easiest model to do if you work through all the maths, but I can show you in terms of pictures what you might want to try. So if you've done the orbit model that we looked at a few weeks ago, it's a very similar force law. So this is Coulomb's law, and it's the law of electrostatic repulsion between our helium nucleus with 2 protons, so 2 times the charge on the electron, and Ze, Z in the case of gold, I think is 79. Hope I got that right. And this is the gold nucleus here. All right, I've just realized that I've used F twice in here. So F is is the coordinate here. I should have used a different symbol for the force. But anyway, if R is the distance between the centers of the nuclei at that particular point, then Coulomb's law is an inverse square one. This symbol at the bottom, epsilon naught, is called the permittivity of free space, about 8.9 times 10 to the minus 12 in standard units. So that sounds like a very small thing. Remember, that's also very small, and so is this. However, you end up with a force. What makes this complicated, of course, and that's what the R hat vector means, is it's along that line. So as our alpha particle gets closer, of course, that force vector will change direction. So doing some sort of numerical method would be good, but you can actually solve this analytically if you wish, although it's not the easiest thing in the world to do. Certainly a little bit harder than doing some of the orbits calculations. But anyway, you end up with this trajectory and you get a kind of closest approach. A nice thing that you will look at in books is the impact parameter. So if you draw a straight line from the, so that line there, remember the alpha particle is initially moving, otherwise it would just be repelled. So it's going down here. It's got 5 mega electron volts. That's its initial kinetic energy. Remember, that's 5 million times the numerical value in joules as the charge on the electron. So that's sort of typical for particle physics. It's mega electron volts, whereas the ionization of hydrogen is about 13.6, so 1 million times less. That's why nuclear physics is important compared to chemistry, because this factor of 1 million, it's 1 million times more energy dense than chemical processes. That's not that chemistry is bad, of course, but this is the numbers involved. All right, so that involved, if you turn that into half mv squared, all right, it's not going relativistic speeds. You can work out the initial velocity, and then it will follow this hyperbolic trajectory. But if you carry that line on, that will be the kind of distance of closest approach, as it were. It's not really because it's repelled, but that parameter you can sort of work out. Anyway, so that will be a really good stretching model, particularly if you're in the kind of upper 6th and you're studying all the guts of this. But it's very similar to orbits. Okay, and look at the sort of scale on this. A femtometer, that's 10 to the minus 12 meters. All right. Okay, so that's kind of model number 1 that you might want to have a look at. Okay, this is model number 2, which usually I teach in upper 6th. Some of you might meet it earlier, but even if you've just encountered this is a good one to do. So this is all about what we call the binding energy. It's known as the V-Zacher formula, or the liquid drop model. That's Mr. V-Zacher. And essentially, it describes why fission and fusion work in the way they do. So nuclear fusion is where we get light elements like hydrogen and helium, well, hydrogen making helium, sort of coming together and releasing energy. Whereas fission, you have heavy elements like uranium and plutonium split apart to produce energy. So all of them, so fission's producing things which have a higher binding energy per nucleon. At the top of that graph, you've got iron. Well, I think it might be another, I think it might be nickel, it might be, just strictly speaking, the highest, but iron 56 is the most common stable element. And that's really interesting because, of course, when you have things like supernovae, all right, it's when you get fusion of increasingly large elements until it gets to iron, and then fusion can't happen anymore. And then the sort of collapsing star bounces, and the shock wave rips it apart, and that's a supernova. All right, so this is all really good stuff in terms of understanding the genesis of elements in the universe. Of course, the heavy elements are produced as a result of that shockwave. That's called nucleosynthesis. So we're all made of stardust, everybody. All of the elements in our body were kind of created at some sort of ultraviolet supernova a long time ago. So what does this binding energy really mean? So if I could sort of highlight, so there's a formula for it, but let's just highlight the thing I'm, can I just confirm that, can you see my mouse pointer? I don't think I can drag a box over it, but can you see it wiggling around?
Yes.
Fantastic. So this is using Einstein's formula of mc squared. So imagine we've got a nucleus of mass, or well, we call it M, but let's say M is the mass. I've also called it M, of A nucleons, so that's protons and neutrons, and Z protons. And that's the sort of the mass energy of it. Now, it contains sort of some other energy too, right? Which is the binding energy. And when I say it contains, if we were to break it apart into its constituent protons and neutrons, we'd have to do B amount of work to do that process. So we can make a kind of energy balance. If I broke up this atom, all right, into its protons and neutrons, I had to add B joules to make this happen. So the mc squareds of all its bits, all right, must be the mc squared of the atom, or the nucleus, should I say, plus the binding energy. All right, so that's an energy balance. And it clearly says that, if I was to break it up, I've got to have more mass, if we divide everything by c squared, than I started with. All right, so maybe a slightly strange idea, but this is an energy balance. It also means we can define what B is in terms of a drop in mass. We call this the mass deficit. So it would be really good if we could actually have a formula for what B is, the binding energy, and particularly B over A. Remember, A is the number of nucleons, the protons plus neutrons. And it turns out this is a good model. So I'll just sort of give you a little tour of the terms. So the first one, the volume one, the more nucleons we have, the bigger the binding energy. So that kind of makes sense. This one is a minus sign, and this goes as the surface area. So if you want radius, if you like, you can cube root the number of nucleons, square it to give you a surface area. So it's a bit like going from volume to radius, to 4 pi r squared. So, and of course, if we have a bigger surface area, that's going to make the binding energy a bit smaller. The next one is that the Coulomb repulsion between the nucleons. So the more protons we have, as big as Z is, the more they're likely to repel each other. So again, that's another minus sign. And then we have some exotic terms. So for good reasons, that if we have more neutrons than twice protons, as it were, so A minus 2Z, so that'll be A plus Z minus 2Z, or A minus, neutrons minus protons. So more neutrons than protons, that might make the atom a little bit more unstable. So that's why that's a minus term. And there's an exotic term, which I don't really understand. So I think you'll ask Professor Chung to explain why that's minus 3/4. But anyway, that's to do with another sort of asymmetry between neutrons and protons. So anyway, it's an empirical model. So in other words, we guess what the number of mega electron volts these are. And you can sort of, take lots of real data and try to fit this curve. But that's not a bad model. All right, so I've plotted it here. So what you could do is you could get a database. A new base is the one that I used. There's probably lots of others off the internet. And you have basically a big table of all, the masses, all those kind of things. And you can plot them on this graph using this formula. So there we go. I've got the new base average, which is blue, and this model, which is red. And they seem to match each other quite well. The reason it's sort of all over the place a little bit is because you've got these extra terms and there are isotopes, etc. But you can work out a kind of average, which is the black bit. And that's the sort of thing which we talk about in our textbooks. So there we go. There's a little picture here talking about the different terms. You can also plot it on a 3D sort of surface. That's a nice thing. You can do matplotlib or mat or anything of the other languages. So what I'm doing is I'm plotting neutron number versus atomic number. And we see that it's not quite y equals x, actually. So there are, on average, more neutrons than protons, which is quite interesting. The sort of line of stability where our binding energy per nucleon increases, and it sort of gets higher here and diminishes. It also gets weaker as you go sort of outwards from that point. You actually plot, so that's real data. So we don't have any data for isotopes that we don't know about. So a neutron number of 100 and an atomic number of 10, as far as we're aware, doesn't exist. There we go. But we can plot this graph with whatever we like. So we've got a nice surface here, so you can kind of see them matching each other. So that's a nice thing you might want to do. Okay, before we talk about any other models, are there any questions in the chat? No? Am I still broadcasting okay?
Yes, yeah, all good. And I was waiting for new questions, but no, nothing pops up. So all good.
So, great. So we've looked at binding energy. We've had a little look at how you might model an alpha particle being deflected by a gold nucleus. Other nuclei are available. Question: do we need to know that equation for the challenge? Well, no. So the challenge, whatever it is, will be released in March, and all the details. You'll get a pack a bit like this with all the physics in it, and probably some demonstration code and pictures that I've done. And so it's like a recipe. Everything should be there. So it's like a recipe, but you also get the food as well. All right. So you just have to supply the cooker, if that makes sense. But you can adapt that recipe as you see fit. All right. However, I would download this presentation and give some of these a go, and you can do that if not right now, when you have some spare time this week. So okay, so we talked about the nucleus. What about the nuclei which are unstable? So this is not fission and fusion. This is about the natural instability of certain nuclei. So this is beginnings of a little exercise I do with my students on radioactivity. So this is the picture of the Chernobyl disaster in 1986. And there's a fantastic HBO kind of film about this. So I'm not sure exactly how accurate it is scientifically, but it's jolly well acted. It's very, very exciting. And it sort of depicts what happens before and after this disaster. And this is where the reaction chamber was that sort of overheated and exploded, releasing a plume of radioactive particles such as iodine-131 and xenon-131. And these are, so iodine, that's a beta minus emitter, so it produces very, very high energy electrons, and xenon-131, which produces gamma rays. The iodine-131, I think, is quite one of the more dodgy ones because that can collect. So iodine collects in our thyroid gland. So if you collected a radioactive one instead in high concentrations, that could be, could be a possible source of cancer. So everyone was taking sort of iodine pills to, if you like, load up their thyroid gland at that time. So this might be a nice activity. You can see that I've got a count rate. So this is the number of counts per second, so decays per second, which is a becquerel, in days, and how that varies. So I've obviously made up this data, but this is, you can imagine, might be what was being collected at the time. So Chernobyl location X123. So if you plot this, you get all these data points. So you notice it's quite random because radioactivity is an inherently random process. So in terms of modeling here, this is interesting too. You could create that graph. In fact, I did. That I generated from a MATLAB program with some random number generators overlaid on an exponential decay. So that's something you could model. You could sort of see if you can work out your own decay curve. This is an Excel sheet. This is a bit busy, so I'll sort of highlight all the main parts. So what we've got, if you want to do an analysis of this, you've got time and activity. You might want to plot it and see if there's a background. And in fact, so this might be a source of natural radioactivity, or indeed, if you're in a reactor or something like this, there might be unnatural rate, but it's not the thing that we're looking at decaying. So you have to subtract the background first. So I've got to, in this particular exercise, you estimate the background and it's set at 123 becquerels. Okay. So you subtract the background And then we want to see what that curve is. So a really good model of radioactive decay, I'm just highlighting the bit at the moment. You may have seen this as a e to the minus lambda t, all right? So whereas, of course, that's equivalent, but I think sometimes it's better to think of a power of 2, because basically what's happening is that in an exponential decay, power law, every half-life, we divide the activity, and in fact the number of atoms, by 2. So what our mathematical formula for the curve, the green one, is our initial activity, sound's background, which is about, what have we got? Well, sound's background is about 884. Okay, so a plus background about 100,007. And you are dividing that by 2 to the power of the number of half-lives, which is our time divided by the half-life. And what we're trying to find in this exercise is that half-life. But as itself, that is a nice way of actually plotting that curve. I've literally used that in the model activity. So I haven't got the Excel sheet up here, but I'm actually evaluating that formula using A naught, which is 957.2. There we go. And a 7.759 day half-life. So how do I find this? Well, if I log both sides of this one, I can get a linear equation. And this is essentially the guts of how we do analysis in physics. You want to turn your graph into a straight line graph, because then we can analyze very easily using linear regression, or literally just getting a ruler and doing a line of best fit, and you're working out the y-intercept and the gradient. All right, so pretty much every piece of experimental work you will do, you're in the business of seeing if I can get a straight line out of it, which means taking your model and rearranging it and see if you can have a y equals mx plus c. So in this case, y is log of the activity and x is the time. Brilliant. And from that, I can work out the half-life. It's minus log to the base 10 of 2 over the gradient. And my initial activity is 10 to the power of c, the y-intercept. And there we go. So that's a nice thing. So that's done completely in Excel. And if you want to get a bronze, if you're really new to programming but keen on physics, you can easily get a bronze. Well, not easily, but with some proper effort, you can get a bronze for the computational challenge, doing everything in Excel. And you never know, you might even get a silver if it's really awesome. But beyond that, it's getting a bit unwieldy to do everything in Excel. So what you could do with this kind of thing is turn it into a data processing pipeline. So this is a screenshot of some MATLAB code. That's what MATLAB looks like. The language doesn't matter, although I like MATLAB. I think you'll get there very quickly. But there might be some Python fiends here. And so I've got some text here. And basically, it's quite human readable. If this is the first time you've joined this challenge, the green stuff means commentary. And on my top tip, if you know nothing else from this talk, is that when you're doing code, write the commentary first. So it's a bit like when you're trying to make a mathematical model, is draw it, write it out in words, and then try and figure out what the maths, and in this case, what the syntax is. So I've got my estimated background, got maybe the font size for my graphs. So I'm going to ingest an Excel file and turn it into a kind of array, which I can use, and that's the code for that, etc., etc. All right. So, and in my code, this is the kind of flow diagram. So in The Social Network, the film where a fictional depiction of Mark Zuckerberg creates Facebook, he draws a flow diagram of how the original Facebook's going to work. And so, that's a really good engineering idea. So we have a program which makes some raw data. So this is using random numbers that creates my Excel sheet. All right. So then I can plot a decay curve. So that's the first bit of code. And then I'm going to analyze this using my MATLAB program. And I'm going to create some graphs. So a line of best fit one and my sort of presentation data. So my data underlaid with my curve that I get from my line of best fit. And all that can be created in software automatically, including the titles, which have, so the half-life I've calculated and I've stuck it in the title. That's a really nice thing. If you just have a graph with, maybe an axis on it, not so useful. Whereas if your graph contains all the calculations too, brilliant, right? And you can just paste that into your paper, your Word document or whatever, your LaTeX, and that forms the basis of a report. So there we go. So you can start in Excel, but I'd encourage you to do some programming to make yourself a sort of pipeline, work out algorithmically what happens next. So here's an idea. You can just use that data. I think if you go onto the Eclecticon, you can actually download it, or you could be even better, make it yourself. Okay, before we move to a next one, any questions?
Yeah, all good.
All good.
Yeah.
Right. So we mentioned that the database of the atoms, this new base database, I've got it in Excel sheet if you download my stuff off the Eclecticon, but as I say, there might be other databases that work. So this is just a nice plotting exercise, really. So this is a graph of the number of neutrons and atomic number, so all the isotopes. And what I've done is I've done log to the base 10 of the half-life for all of them. And it's really fascinating. So why do I do log to the base 10? Well, because the half-lives vary from 10 to the minus 10 seconds to about 10 to the 15 seconds. In other words, about the age of the universe, completely stable. So iron 56 doesn't decay. Well, not on our scales anyway. Maybe in the Planck time or something like this. 1 over the Planck time, rather. Anyway, so what I've got is y equals x. So that's protons equals neutrons. And you'll see, apart from very light elements, and the black lines are basically really stable ones, the sort of plot of the isotopes deviates a bit from this, and particularly as the elements get larger. Really fascinating. But I think the most interesting thing is if you go along that line, kind of a ridge line, if you like, you go from blue to black almost by just adding a neutron. So what that means is that the stability of your nuclei and your isotopes is really a really complex relationship. So in other words, if you have I don't even think there is a formula, correct me if I'm wrong here. So if I say Z protons and A minus Z neutrons, what's the half-life? I don't think actually we know how to do that. And that kind of indicates that even if we did, that would be a very, very complicated thing to do. You get sort of islands of stability and other islands of instability, or kind of pits of instability. Something that's a bit more tractable, perhaps, is the decay mode. So this is something that hopefully you should be familiar with, that we get beta minus decay, and that's for the ones where we have more neutrons than protons. And that kind of makes sense because that's what beta minus decay is. It's a neutron that decides one day to be a proton and an electron and an electron antineutrino, which of course the electron and the antineutrino escape. That's what a beta particle is. But we also can have beta plus decay, which is the other way around. And that's going to be when protons and neutrons are more similar. So the green splodges, although that's not uniform. There's a kind of area in the middle. For heavier elements, we might be able to spit out an alpha particle, a helium nucleus. That's clearly not going to happen for lithium, but it will happen for, say, uranium, plutonium, that kind of stuff. Though interestingly enough, you do get alpha decay all the way down to about atomic numbers of 70, something like this, which is quite fascinating. And there we go. And there's a few others as well, other measures. So that's quite a nice, almost like a geological map of how your decay modes work. Okay, I'm going to move on to something slightly different. So one of the things about quantum mechanics is that it's basically based on several experiments that were kind of in the more esoteric end of things at the end of the 18th century, end of the 19th century, that couldn't be explained properly by classical physics. And good for science, rather than just glossing over these things, trying to explain them absolutely revolutionized physics. And one of them really is kind of more basic than that, is that actually is to sort of think about how we relate gravity. This is the law of gravity of Isaac Newton. So the product of the masses, inverse square law. R is the distance between the masses, and G is the kind of thing which turns mass and distance into force. That has a very similar rule for electrical things. Of course, we can have positive and negative charges, whereas as far as we're aware, we only have positive mass. And so positive masses repel, but opposite charges attract. So this is Coulomb's law. We've already met this. And And so you might think, well, okay, it's just the same kind of thing, right? An electron will orbit a nucleus just like the Earth orbits the sun. But we have a problem here. Because if you're using a mobile phone or listen to the radio, you know you can transmit energy. In fact, or you've had a suntan, you know that electromagnetic waves travel through the vacuum of space and transmit energy. So where's that energy come from? Well, it comes from the electron, all right, which is accelerating. Why is it accelerating? Well, it's going around in a circle, and accelerating charges radiate. So next slide is very mathy. Don't worry about writing anything down, just to know that this calculation is possible. So if you really want to go through it step by step, you can download this calculation. I just want to show you how you might do it and then what the number is. So hold on to your hats, ghastly. It's beautiful actually. But basically, the thing at the top is called Larmore's formula. And interestingly, the rate of change of energy, which is power radiated, goes as the square of the acceleration. Not the acceleration, but the square of it. And you can work out using Coulomb's law, all right, what that acceleration is, okay? And you get a kind of complicated looking formula for the power radiated by a rotating electron around an orbit. Now, you can kind of shortcut this by saying, all right, if I can work out the kinetic energy of my electron and divide it by this formula, that is basically the time it takes for my electron to inspiral into my nucleus. And if you put all this together and do lots of algebra, which looks like this, you get a really small amount of time, which is about 4.7, let's call it 5, or let's call it to an order of magnitude, because I've made some approximations here, but it's about 10 to the minus 11 seconds. Disaster. We shouldn't exist. All right, so the electrons and the protons should all have coalesced a long time ago, about this amount of time after the Big Bang, or maybe a bit later when, protons and electrons somehow separated. They'll all have joined together and we'll just have radiation. Oh no, so we shouldn't exist, because we need separated charges for electrostatic repulsion, for the operation of cells, for all the structures that we have. Life should not exist, which is a big problem because it does, obviously. So how do we solve this? Well, the idea is that we can think of electrons as being waves, standing waves. And the Bohr model from Niels Bohr is that electrons form a kind of wave around the nucleus. And that gives us the quantum in quantum mechanics, because 2 pi r is going to be a whole number of these wavelengths. So it's somehow discrete. But what are these wavelengths, right? So I've given a bit of text here, but basically this is the kind of starting point for quantum theory. So why do atoms exist? To kind of answer this fully, all right, you've actually got to look at 3 completely different things. And these may not seem related to what I've just told you, but they are. They will provide the kind of physics ingredients to explain that question. And ultimately, if you're doing this yourself, is to build the Bohr model of the hydrogen atom, which is something I did when I got to sixth form, and I'd recommend all of you do this before you go to university. All right. You might need to learn a few bits and bobs from books, but it's a really good thing to do. And I'll give you the recipe before the end of the talk today. So there are 3 ingredients, really, 3 experiments. One is the spectrum of radiation from a hot body. We call this black body radiation, but that's kind of ovens and things. It also works for stars, which are not really black. Okay, not from a black hole, perhaps. There's something called the photoelectric effect, which I've literally just done today with my 4th years. Hello, if you're on the call. And the spectral lines of hydrogen, which is a lovely, lovely experiment. And if you do these experiments and you try to explain them, you end up with some really profound ideas. So one, all particles have a kind of wave-like characteristic. These waves work like waves you've met before with sound waves, light waves. They interfere, they diffract, they in fact tunnel through barriers. That's something that might be more mysterious to you, because these waves are related to the chance of finding particles. So this is how an electron can tunnel through various electrical components in a computer chip. So I'm pretty much guessing that quantum mechanical tunneling is happening probably multiple times on multiple devices right now for all of you, certainly in your computer. And And yes, so this wave pattern is related to probabilities, chance of finding things. And that means uncertainty is completely built into physics. And that's Heisenberg's principle. I don't know if we'll get to that today, but it's at the end of the presentation pack. So here's number one. So I've just got a couple of little ideas of this, and there are some models that you can build. So firstly, a little law of physics. So here's the sun, 5,778 Kelvin. All right, that's how hot the surface of the sun is. It's much hotter inside. And it has a ridiculously large radius, about 100 times that of the Earth. And it produces a wattage. So L stands for luminosity, but that's the number of watts it produces, which is ridiculous. It's 3.85 times 10 to the 26 watts. Now, if only we could harness all of that, eh? Actually, does anyone know in pop culture, or perhaps what that's called, if you could build a mega structure around the star and harness all its luminosity? Anyone want to? Yes, you're on the money here. Dyson sphere, excellent. So if you've watched, I think it's one of the Marvel films, I think they use this for, I think it's one of the Thor films, something like this. Anyway, this works on the basis of something called Stefan's law. So the intensity, which is the radiation per square meter, interestingly enough, goes with the fourth power of the temperature in Kelvin. And the number in front of it is called the Stefan-Boltzmann constant. And if you've got something which isn't a star, but like, a human, or a human draped in a silver cape or something like this, you can have an emissivity. So if you're in a silver cape, the emissivity is very small. If you're in a sort of a matte black cape, like, if you're in the Matrix, that's going to be closer to 1. So there we go. So I think at 20 degrees Celsius, if you run this formula, it's about 418 watts per square meter. So that's probably what you're radiating right now. Whereas on Earth, of course, we're so we're an astronomical unit away. If we divide the luminosity by 4 pi r squared, we get about 1361 watts per square meter. So that's the maximum power a solar cell could actually deliver if it was 100% efficient. So 1.4 kilowatts per square meter. All right. So you can boil a kettle if you or run a microwave off a square meter if you were in space. Okay, so if we take this light, the light from a star, and split it up using a spectroscope, so basically a prism, and split it up into different wavelengths, the waves will disperse or refract in different ways, you will end up with a curve. And so this is wavelength, going from a sort of ultraviolet all the way to the infrared. And it's got some interesting units. It's sort of watts per square meter per wavelength, in this case per nanometer. And the yellow one, I hope you can see that, that's what you get in space. And on Earth, it will be the red one. And you notice there's some holes in it. This is because different molecules absorb radiation preferentially at certain wavelengths. It's another big hint that these electrons inside oxygen or water have certain energy levels. So the electrons aren't any old kinetic energy, any old orbit, if you like. They have discrete energy levels. Another quantum mechanical idea. And we can see that by these little dips. And in fact, you can characterize molecules by which wavelengths correspond to where they absorb radiation. Right? So this is how we can, look at the composition of stars, which may be hundreds, if not millions of light years away by their spectrum of light. So Max Planck and others were trying to figure out what this curve was. And no one was able to do this successfully. There's a group called Rayleigh-Jeans, Lord Rayleigh and James Jeans, I think, who actually went to my school, so Winchester College a long time ago, and they were able to predict the curve, the sort of long wavelength bit, but it just got bigger and bigger and bigger, and so ended up with something called the ultraviolet catastrophe. So obviously that's not what we see. We don't have our faces burnt off with UV, so no one could really work this out. Anyway. So the idea, the area under that curve is indeed this lot, the total intensity. So what is the curve? Well, Max Planck was able to work this out. Here we are. This is a young Max Planck with a fantastic monocle. I know, actually, it's a pair of glasses, but he's looking very suave. And the curve is quite complicated. It's got an exponential in it. It's got temperature. It's got a fifth power of the wavelength. This is a really good bit of maths to work out, but not for today, but perhaps between now and the next 2 years. I've got it all written out if you want. So if you're on your first year at university, go and have a look at my website and you can go through the derivation of this. It'll also be in Science by Sim 3, which will be published in a few years. Now, the story is complex, but basically, in order to get this curve to work, Max Planck had to, well, actually, Albert Einstein, should I say? I think he did the derivation. He had to quantize energy. Now, what does that mean? It means that electromagnetic radiation comes in energy packets, which are discrete, and their energy is a very, very small number times the frequency of the radiation. All right, so this is the sort of one, if you want to learn one formula about quantum mechanics, this is the one you need. All right, this is the energy of a photon. But it all came about to try and predict the shape of this curve. So that's a pretty weird idea, but it's very useful. And how can we use this? Well, a classic experiment which you'll all do in various guises at A-level, if not before, and that's called the photoelectric effect. Let's check some time. Before we get into that, any questions on the last couple of ideas?
Seems all good.
So the programming project here would be download this data. So this is some satellite. Again, you can get this from my website and then plot that. All right. So that's quite a complicated little formula, but you could devise a bit of Python or MATLAB or Excel to plot what that looks like and vary it with temperature. That might be an interesting thing to do. That'd be a nice challenge. So this is called the photoelectric effect, and basically it works like this. This is the kind of experiment by Robert Millikan. Okay, also the famous Millikan experiment for working out the charge on the electron. I think University of Chicago. Someone want to correct me if I'm wrong on that one? Have I got that right? No one's saying anything. Let's assume. Anyway, he's an American. So the idea is you have a kind of evacuated cell. This is like a cylinder with no air in it. And you've got a metal plate and a metal plate. Now, we're going to call this the one on the left-hand side the cathode, because that's going to produce electrons. That's what a cathode is. It's not necessarily a negative or positive. It's a source of electrons, which used to be called cathode rays. Now, what you do is you get a lamp of a certain wavelength, and if it's like, I say, desk lamp, you'll put it through a filter to give you a certain wavelength. And what you find is that no matter what you do at low wavelengths, electrons just, nothing happens, all right? We don't get any electrons popping out. But above a certain frequency or below a certain wavelength, like blue or ultraviolet, suddenly we start to get electrons emitted from this. And if you connect this up to a battery with an ammeter, you'll get a current, all right? Now, what you want to do, and this is what's really clever about this experiment, is that you change the sort of, I put a voltage across it, an EMF, the wrong way around, okay? So you get a force, so you make this plate, the one that emits the electrons, to be positive. So the electrons, in a bit of kind of a bungee run style, so imagine, you know, you've got a bungee cord attached to you and you run away and it pulls you back. Well, that's a bit like this, that we have a force on the electron. It's actually the voltage divided by the distance here. That's the electric field strength multiplied by the charge, and that's the force on the electron. So that means you can do work, force times distance, which is the charge on the electron times the voltage. And hopefully that makes sense, because voltage is energy per unit charge. So EV is the work we do on the electron. And what we want to do is kind of work out V to be just enough so no electrons get to the anode. In other words, our current, which we put our photocurrent, and the electrons that are produced, goes to zero. And that means that EV is equal to the maximum energy of the maximum kinetic energy the electrons emitted. So the maximum. So we have a model of this, and it involves basically a one-to-one balance of photons and electrons. Okay, so that's the maximum kinetic energy of electrons, which is the photon energy minus some penalty to get out of the metal, and that's the minimum amount of work to get out of the metal. I say minimum and maximum here because, you know, it might take a bit more energy to get electrons out, and so, you know, not all of them will be will get to the end. But once we wind the current down to zero, we've looked at the fastest ones, those with the highest energy, which is when this energy balance works. So we can measure the voltage quite easily. All right. If we know the charge of the electron and we know the frequency, or indeed the wavelength of light, so c over lambda is frequency, we can plot a graph of v versus f, and that should be a straight line graph with Planck's constant over E to be the gradient. So if we know the charge of the electron, we can work out Planck's constant. And it's amazing. I did this in about 20 minutes this afternoon with my fourth years, and we got a graph like this. Perhaps not quite as straight as this, but it wasn't too bad. So there we go. And this has been nice thing for you to plot, maybe something like in MATLAB or Python, literally. And so we'll get data along here in the purple region. So at 0, you extrapolate that line, so V versus F, all right, you'll work out what W over E is, hence what that work function is, the minimum energy to get out of your metal. And from the gradient, you can work out Planck's constant. So there we go, amazing. I think we got about 30% of the answer because our little cesium cell, I think, has got a little gotcha in it. But in principle, this is how you could do it. And the work functions are rather small. They're not too far off the ionization energy of hydrogen. So there we go. So this is an amazing experiment. I think Albert Einstein possibly won the Nobel Prize, I think, for explaining this. And it really shows that photons exist. So the next one you might do is look at hydrogen spectra. And I think we are getting close towards the end. So I think maybe I'll stop here and I'll take any extra questions at the end. So we won't do electron diffraction. You can have a little look and see what that's about. So the spectra of hydrogen is really interesting. So this is Johann Balmer. I think was a Swiss maths teacher. Yes, go for it. So there are, I think, 2 teachers in the pantheon of physics, Johann Balmer and I think Mr. Ohm. I think he was a kind of what we would call a physics teacher. So anyway, it's known for a while that when you look at hydrogen, the light that's emitted from hot hydrogen, and you split it up in a prism, you don't just get any old lines. All right, there are very discrete frequencies, or wavelengths in this case, that the light ends up at. So you get, the Balmer lines are the ones in the visible spectrum, and there are others too. If you were to look at it in the infrared, or indeed in the UV parts of the spectrum, you'll get these lines. And indeed, it's the opposite. If you absorb light, the hydrogen will absorb light at very discrete wavelengths. So Johann Balmer, story goes, analysed these lines. So discrete lines, that's just like a brilliant puzzle for mathematicians. And he ended up proposing a formula for this, which involves the difference of the reciprocals of integer squares. Amazing. I would love to know how he worked this out. And in fact, it's to the -1 as well. So it's an extraordinary piece of work. Multiplied by a certain wavelength, 91.13 nanometers. And for the Balmer ones, the visible ones, n here is bigger than 3. And I forgot that the right way around. Yes, so that makes that smaller. And m is equal to 2. So you get different lines when m is 1, etc., etc., etc. So that's interesting, isn't it? So you can derive this, and this is something called the Bohr model of the atom, which I recommend all of you do. So the next big ingredient of this is how you work out a wavelength for a particle. And this is called the de Broglie wavelength, and it's named after Louis de Broglie, who was a rather aristocratic physicist. And I guess we should put Niels Bohr into this as well. So this is the most boring model in the world, of a hydrogen atom. And it's to get around this problem of electrons radiating in about 4 × 10⁻11 seconds. So the idea, I've got a sort of wave here, which I've fitted around a circle. All right. In fact, that's what if you want to plot that, that's how you do it. A sine n theta plus b. And for waves to fit, 2πr must be a whole number of wavelengths. And that's the quantum in quantum mechanics. So the de Broglie wave relationship is really interesting. And I'm just going to state it today. But I don't think we got there quite with the relativity course last week. But you can, something called the energy momentum invariant. That's a nice way to think about the de Broglie relationship. Although the more you think about it, the more mysterious it is. Essentially, the momentum of something, I've used a classical momentum here, could be relativistic if you're going fast, is Planck's constant divided by the wavelength. Or the wavelength is Planck's constant over the momentum. So there we go. We've got E equals hf and lambda h over the momentum. So those are your kind of key quantum equations, if you like. And it means that angular momentum, if you've studied this, mass times the radius times velocity, is quantized. All right, and that's a sort of a measure of sort of, in a rotational sense. And h bar, if you come across it in literature, is literally Planck's constant divided by 2 pi. It props up so often that it's given a special notation. So I think the next slide is quite mathy, so I'm just going to give you a little bit of a tour of various bits. All right, here we go. So what you've got when you do classical physics for electromagnetism, you work out a formula for the energy of something rotating around in a circle. All right, it's 1 over r, so not 1 over r squared, that's force. So energy goes as 1 over r. And you do things with circular orbits, etc. And if you put that together with de Broglie's idea, you end up with a formula for the energy of your electron orbiting. So in hydrogen, it's minus 13.6 electron volts over the square of an integer. All right, so these are the energy levels of hydrogen. So the lowest level is minus 13.6, and then we have less negative levels as n gets bigger. So n can only be an integer. And then the difference in these is what gives you your photon energy. So when electrons go from a lower to a higher energy state and back again, we can emit photons. And if you basically do that, that gives you the difference of the squares of integers. And if then we want wavelengths, we have to invert that. So that's how you derive the Balmer formula. So basically, in summary, you need to work out a model using classical physics for the energies of your rotating electrons. We then combine that with de Broglie's relationship. The momentum is Planck's constant over the wavelength. And if you put that all together, you end up with this. All right, so that's how you derive your Balmer formula. And of course, the first thing you want to do is plot it. And here we go. So I've got, so these are the names of all the other series. So Balmer's the red one. So Lyman is the UV one, and Paschen, Brackett, and Profund are kind of in the infrared parts. And so, you've got sort of discrete energies here versus wavelength. And there we go. That's your sort of your formula. So that's a really good thing to sort of work and do step by step, putting all that stuff together, assembling a quantum mechanical model. It's obviously not the last word, but perhaps the first coherent word of quantum mechanics. So I think that's a pretty good place to stop. No, one more thing. So here's a nice result for you to think about. So I've kind of given the game away here by asking how big could atoms be? How many protons could you have in an atom? And maybe if you, I think it's clearly not 200 or 400 or 500 from our isotope diagrams. And the number's not quite as high as this, but it could not be, with classical physics, bigger than 137. Why is this? Well, if you do your Bohr model, you've got quantization of angular momentum, which means the speed of your particles is a whole number, nh over 2 pi, all right, divided by the mass of the electron and the radius of the orbit. And if you put it in the mass we had before, it turns out that the velocity of my electron is the speed of light times the number of protons over an integer multiplied by a number. And that number is dimensionless, okay? Because we've got speeds on both sides. That's just the number of protons. That's just the quantum number, all right? And the biggest V could be is when n is 1. So if you've got hydrogen, for example, that Z is 1. So how big could Z be? Well, clearly our velocity can't be bigger than the speed of light if you came last week. So what's alpha? Well, alpha turns out to be about 1 over 137. It's called the fine structure constant, and it involves all the other constants and gives us a fraction of a very moderately sized number. So there we go. 137 is a very important number in the world because its reciprocal is this. So if Z was 137, according to this model, then the speed of my electron would be the speed of light, which we can't have. So therefore, we can't have any atoms with more than 137 protons, because that would mean the electron's going faster than the speed of light. Now, this isn't quite right, of course, because if you put z equals 1, electrons are going about 1% the speed of light anyway. So it's not going to be quite like this. So 100 and something. So what we're up to is 112. Does anyone know the largest? What's the largest atomic number? I'm just going to Google that myself, actually. Organessen, which is 118, I think.
Yep, people are agreeing.
Yeah, 118. There we go. I think that was also, wasn't that an advert for a kind of phone thing? Wasn't it 118? Oh, there we are. So we need a 119. But anyway, there we go. So I think that's a curious place to finish. Do we have any general questions? Otherwise, I think that's going to be it. Yeah, we're at 9 o'clock.
Yeah, all good.
Fantastic. Well, thank you very much, everybody. That is a course which normally has probably about 30 hours of lecture courses that we've condensed into one. Congratulations. Do download the presentation. Find one of those things you thought was fun. Probably the simplest might be, I don't know, plotting the Planck spectrum, or I don't know, doing one of the radioactive decay models in Excel, something like that. If you fancy some graphics, download the new base or plot the VSACA formula for binding energy. That'd be a cool thing to do. If you're find a real challenge, and go through the maths of the Bohr model, plot the graph, or make a dynamic model of, say, the alpha particle kind of being repelled by a gold atom. So there's loads of ideas. Pick one of them and have a go. All right, I'll see you next week.
Thank you very much. Let me just reiterate that this is a smorgasbord of delights. It is not possible for you to understand everything in real time and be able to do everything. This is just something that you can use as a tasting menu. I'm sure there are a few ideas here which are worthy of your consideration. So if you find any particular idea particularly interesting, then we want you to use this as a launching off point for your own investigation. And because these equations are hard, the better way to do it is to use a computer to do a bit of programming. And it doesn't have to be very complicated. It could be as simple as using Excel to try and plot a graph, maybe the semi-empirical mass formula there, and see what sort of shapes it gives you and what sort of predictions it gives you, and connect that with your periodic table. It could be simple, it could be more complicated. Okay, thank you. See everyone next week.